welcome to this video. Today we're going to prove that Archimedes' law for floating. So when you put an object into, let's say, water, how do you know if it's going to sink, float, or maybe just stay in its place? So we're going to find Archimedes' law for that, and then we're also going to prove two more problems that relate to this sort of thing of objects floating. So here's what we're gonna do. First thing we're gonna do is look at let's say like a pool of water, or like a container with water in it, and then in that water we're gonna look at a cube with sides A. And by the way, this doesn't have to be specifically for a cube, it works for any object, but I'm doing it for a cube just to simplify things a bit. So we're going to have A, and this is a cube of water. And now, we're going to look at the forces that are being done on this water. So on this cube of water. So there are three things. No, there are two things: water pressure and gravity. Gravity, we know, is just mg. And we don't know what the mass is yet, but we can easily find it. And then there's water pressure from all around, from all around it. Now, don't be tempted to say that the water pressure cancels, because it's not true. The water pressure up here will be lower than the water pressure down here, meaning that it will be probably pulled up by the water around it. Now, and so we're just gonna call it Fw for force of the water, and I'm gonna call the sum of all those forces that F water. Fw, I'm not going to write to draw it, because it could be like this way or this way or this way or this way. We still don't know. But what we also know is, obviously, if the water is stationary, that means the cube is also stationary and it's not moving, because it has no reason to move, because it's just a cube of water inside water, meaning that we know the sum of the forces applied on this cube is 0. But we also know, if we say the x-axis goes up, and we know there is minus mg, but then there is plus Fw. And now we can also see that Fw has to point up, because Fw can point to any side, left, right, whatever, because then the cube of water would be moving to a certain side, which obviously isn't the case. Again, it's stationary. And it also has to cancel with the mg, meaning that it has to point the opposite way of mg, which is up, which is just like we expected. So minus mg plus Fw, that is the sum of the forces applied on this cube, which is 0. Meaning that the force, the water, is mg. Now, we want to find what is the mass. So we're going to write g times, so we don't know what the mass is, but what we know is it's a cube of water. And we know the volume of the cube, it is a cubed, a times a times a. And so, we let's call the density of water sigma, and then we know that the density times the volume will be the mass, meaning that this is G times density. So if we have a cube of water with size A, then the force the water is applying on the cube is G times sigma times A cubed. But we can also realize that it doesn't matter. Whether the cube is made of water or steel, or wood, or anything else, because the force of the water can only be changed by the shape of the object. The object's mass cannot change it. The water doesn't suddenly feel whether the object is made of wood or steel. It will apply the same force. So now let's erase this, and we know the force of the water is G times sigma times A cubed. And now we'll look at not just a cube of water, but just any cube with sides A so any cube with sides A, now it has a certain mass M in the water. Now we know it doesn't have to be stationary, but we know, again, the forces applied on it are mg and Fw. So the sum of the forces, we don't know if it's 0 or not, but we know it's Fw minus mg. But now we know what Fw is, because again, the water will apply the same force. It's only dependent on the shape itself. So all we need to do is so we need to just plug Fw in. So we found out it's G times sigma times A cubed minus mg. And now we know, so now let's see. We know if it floats, then the force the water is applying has to be bigger than mg. So the sum of all forces has to be bigger than 0. So for float, it is required that the sum of the forces will be bigger than 0. But now we know what the sum of the forces is. So this means that we'll take a G out from this subtraction. We'll get sigma A cubed minus M is bigger than 0. And now we can cancel G and move M to the other side to get that M has to be smaller than sigma A cubed. But now we can divide by A cubed to get that so we'll call it sigma W, so the density of the water is bigger than the density of our mass M. And so, if the density of this object is smaller than the density of the water, it will float. And then you can easily see that if this object's density is the water's density, it will stay in place. The sum of the forces will be 0. And if the density of the object will be bigger than the density of the water, it will sink. Again, it will sink. Again, just looking at whether the sum of the forces is now equal to 0 or smaller than 0. So this is our law for floating. Now, so this is Archimedes' law for when does an object float, and it doesn't have just to be in water. It can be in any substance whatsoever. So for example, a helium balloon floats in air because the density of the helium balloon is smaller than the density of the air around it, meaning that it will be pushed up. Which is why helium balloons float. So now we can erase this and look at our second problem. Our second problem. Okay, so now we're gonna look. So now let's assume that the mass floats. So we put it in the water. It went up and then bounced a bit, and then eventually it settled. And now it floats above the water, stationary like this. So part of it is inside the water, part of it is outside the water. And we want to find when, at what height, so say this height, which we'll call it y, what portion or so what height of the cube is inside the water. Okay, so here's what we're gonna do. We're gonna look specifically at the part that is inside the water and the part that is outside the water. So the part that is inside the water, we know it's something like this. When this is y, this is a, and this is a. And we know that there are now three forces applied on this object. First of all, obviously, we'll call it, so small mg, down. Next is the force of the water, again, because it's still in water. So the force of the water up. And then there is also, because it's a part of the entire cube, we know that it and the part of the cube that is outside the water are touching, meaning that there is a normal force between them. And so, this is N. And now let's look at the part that is outside the water. So we have something like this. And now this height is a minus y. This is a and this is a. And now, because this is outside the water, we will ignore pressure from the air and all that. But what we know is now this, and there are only two forces applied on this. There is big M minus small m g, and this is the mass of this object, because the mass of the entire cube, we can mark it as big M, and we marked the mass of this little sliver of the cube as small m, meaning that the rest of the cube has to weigh big M minus small m. And so this is the force down, and then upward there is still that normal force, because these two are touching in our scenario. But now we know both of these so now we know both of these are stationary because our entire cube is stationary, meaning that we can derive two equations here. N is equal to big M minus small m g, and Fw equals mg plus n. And now I can substitute the normal force into here to get that when we put m into our brackets, it cancels, and we get big M times G. And now we know the force of the water that is applied only on this lever, only on this box that is a part of the entire cube, has to equal mg. But now we know the force of the water is, okay, so we know from previously that the force the water is applying on an object is its volume times g, the gravitational acceleration downwards, and multiplied by the density of the water, meaning that this is g times sigma water times, now the volume previously was a cubed, now it's a times y, which is a squared y. And we know these have to be equal, meaning that we just need to solve for y. So we'll divide by this, so we'll get y is equal to m over sigma water a squared. Notice that g cancelled out. And now we can look at m as the volume of our mass, which is a cubed, multiplied by its density. So this is a cubed times sigma m divided by sigma w times a squared. And now we can cancel out a squared to get that this is a times the density of the mass divided by the density of the water, which is a result that actually makes sense. Because note that previously we were told our mass m floats, and then it was in the water, and then because it floats, it went up, and then it bounced a couple times until it eventually settled. But so we know that we did all of this with the assumption that our mass m floats, meaning that sigma m is smaller than sigma w, meaning that this value is smaller than 1, meaning that this value is smaller than a. Which perfectly makes sense, as y has to be a small part of a. Because y is a part of the entire length a, so it has to be smaller than it. So now this is our second problem related to floating, and now we have another final problem, which I think is the most interesting of the three. Let's say you have a glass of water with an ice cube floating inside it. So it's like before, it's a certain height from the water and it just sits there. Next, after you wait enough time, eventually the ice cube will melt and it will turn into more water. Question is, will the water level rise? Will the water level rise, or will the water level be higher or lower or stay the same? So that's what we're gonna figure out. So first thing we're gonna do is look. So we know the height level rises based on how much volume is added to the water. Meaning that question is, what has more volume? This sliver when it's ice, or the entire cube, but when it melted into water. So turns out they're the same. So here's what we're gonna do. We're gonna call the volume of this part here that's underwater, that adds to the level of the water, we're going to call it V1, and we're going to call the water, and we're going to call the added volume after the ice melts. So this is the previous one. Let's say it rose by, and then it rose by some amount. We're going to call this V2. And we're going to calculate both of them. So V1 is easy to calculate. We know it's just we know, like before, it's a part of it's a part of the cube when this length is y, this a, and this is a. And we already know what y needs to be for this ice cube to stay in place. We know that y has to be a multiplied by the density of our ice divided by the density of our water. And so I'll call this for short, sigma I divided by sigma W, which means that V1, which is just a times y, is equal to a squared y, which is a cubed sigma I over sigma W. So this is, so we easily calculated V1. Now let's look at V2. V2 is a tiny bit trickier, but it's still not that hard. So we know that what happened when the ice cube turned into water. Its density changed, but its mass had to stay the same. Meaning that the mass of the added water and the mass of the entire ice cube has to be the same. And so we're going to look at it as a cubed, which is the volume of the ice cube, multiplied by the density of the ice, which is equal to the mass of the ice cube, which is the mass of the added water, which is V2, the volume of the added water, multiplied by the added water, multiplied by the density of the water. And then we can just, to solve for V2, we just divide by sigma W to get that V2 is a cubed times sigma I over sigma W. And look at this, we got that they're the same. Meaning, which also means if you have certain, hypothetically speaking, let's say you have icebergs in the ocean, and let's say for some reason the earth starts to heat up, causing the icebergs to melt. Because we know the icebergs are floating in place, we know that when they're melting, it still won't change the level of the water based on what we just did here. Meaning that water level rising in oceans is not caused and isn't really related even to icebergs melting in the ocean. Because again, like we just calculated, when an ice cube melts, when an ice cube floats in water and then it melts over time, the level of the water will still stay the same. So, that's our final problem. So that's it. If you want more content like this, please subscribe to my channel. I'll be uploading more interesting content and things like this in the future. And finally, that's it.